it's really nice to be here. I hope this goes well. So I'm really happy to be here. So I'm going to talk about a lot of homological algebra today. That's kind of crazy because it's got all this algebra structure too. And I want to say a few things before that. So, I mean, this is a very large group, and you're all at like different levels in your education. And then even more so, you're coming from different directions. Some of you are probably more, I don't know who you are. Some of you are probably more geometric, right? And some of you are probably algebraic. But then within algebra, do you like ideals and powers and things? Or do you like homological algebra or characteristic? I don't know. Or maybe you're a younger student and you don't know yet. So I have no idea. So some of this stuff might be boring for if you've seen DG algebras. I'm sorry to that, because the rest of people haven't. And but mostly I'm worried, like, if it's just not making sense, something like why are you multiplying those? Just like why? What? Just please stop me and ask. It would make me very happy. Okay? Because otherwise I have no idea what's going on with you. All right. Okay, so I'm also really terrible with two things. One is names. So I'm going to ask you all your names all week and remember 0 of them. But I'm really happy to see you. And I remember people, but I can't remember names. And the other one is I'm terrible with time. So I set my alarm for 1 hour and then I have longer, an hour and a half sort of. Right. So if the alarm goes off, don't get scared. Okay. All right. So, and also if I end up not writing big enough or you can't hear me, please tell me in the back. Okay. All right. So today, lecture 1 is going to be on DG algebras, and I'll explain that word. Okay, but before I start, I want to make sure that we're all on the same page. So, okay, first let me ask you, who knows what a complex, a chain map, and a quasi-isomorphism are? Can you raise your hand? Who does not? Don't be embarrassed. I need to know. Good. I'm going to define them. Okay, good. And who has seen what a DG algebra is? Okay, good. That's good. I don't want you to have seen. Who has seen Tate's construction of the resolution where you join variables? Okay, so that's what I'm doing the first 2 lectures slowly. So some of you might be bored, okay, but that's okay. But most of you haven't. That's great. Okay. Okay, so very quickly, just let me just tell you pre-stuff. So given in R module M, also I abbreviate a lot. So if you don't know my abbreviations, just shout. What is that? Modules. Okay. So in R module M, a free resolution, which I'm just going to write RESN. So a free resolution is an exact complex, which I'm just going to write CX of 3 R modules. So it looks like, so you start with M. I know you mostly know this, but I need to say it anyway. So you map a free module onto M, right? So this is a free module. You take generators of M. You take a free module of this on a basis of the same size, and you map it onto there. Then you look at the kernel. That's the kernel of that. So that's a short exact sequence. And now you take generators of the kernel, and you map onto there. So this is onto a free module F1. 3. And then you take this composition, and that's the first differential. So differential sub 1. And this map at the very beginning we usually call epsilon. Okay, and then you repeat. You take the next kernel of that, you map a free module onto that, and then you take the composition, and that's the second differential, and then you continue forever. Okay, so that's the three resolutions. Some of them end. At some point, you get the kernel as 0. You get 0, 0, 0, 0. And some of them are independent. Okay, and so Ki, which is the kernel of delta I, yeah. So the elements in the kernel are called cycles, and the elements in the image are called, so the image of each delta are called boundaries. So if I use those words, that's what they mean. Okay. And one more quick review also is, and sometimes you chop the M off, and just the F is the resolution. All right. But this is an exact complex. What if it's not exact? You have a non-exact complex. Those are also interesting today. Okay, so a sequence of R module maps. Map means homomorphism. Homomorphism. Okay. Dot x2, x1, x0, maybe it continues, boundary 1, boundary 2, is a complex if boundary squared is 0. So you do the boundary twice. You do boundary, and the composition is 0. Which means that the image is contained in the kernel, so you can define homology. So the n homology, Hn, of the complex X, this whole thing is called X, is defined to be the kernel of boundary n over the image of boundary n plus 1. Okay. One more thing. So definition, a map, so any map from X to Y is, with, let's call the map phi. So if you do phi and you do a boundary, or you do boundary and do phi, it's the same as boundary phi. It is called a chain map. And it's called a quasi isomorphism if the induced map on homology, so that's Hn of x goes to Hn of y, is an isomorphism for all. Okay. Okay, so question.
X and Y are complexes.
And X and Y are complexes here. See? Complexes. And when I map from one complex to another, you have X written out, you have Y written out in 2 long rows, and you get a bunch of maps between X2 and Y2, X1 and Y1. And this is saying that the squares commute. Okay, so this is classical homological algebra. So if it's new to you, you might want to look at just the classical homological algebra book by tomorrow to read some of the background. Any source. Okay. Well, what we're doing today is completely different. So we want a complex that also has a multiplication on it, which is much harder to get. So let me say something. So, to understand algebras, so that means, like, for example, you have a map from R to S is a ring map, and you want to resolve S as an R module. But you kind of want to resolve it a little better with some algebra structure also. Okay? So then one wants to consider, well, you would do this, you would make a free resolution, but I want a product, I want the algebra, I want the, it's not a, S is not just a module, it's a ring. I want something about why it's a ring, not just an R module, to be reflected in the resolution. So one wants to consider resolutions that have some algebra, which means like ring, structure to them. And that otherwise it's not, you're not reflecting the algebra information at all. Okay, now the problem is, with this is, that if you're just looking at modules, this procedure is wonderful. In fact, the whole category of R modules is an abelian category, which is why you're allowed to think about kernels, exact sequences, and all these things. But so the problem is that the category of R modules, so R mod, is an abelian category, which means it has kernels and exact sequences, but like algebras is not. So we have no kernels, we have no, you can't resolve in the usual way. Okay. All right, so before I continue, I think I wanted to say a couple of things. So I'm going to give you the definition of how we're going to resolve, or what the resolution looks like. But I want to tell you that this problem of wanting to include the ring structure goes way back. And a lot of it goes back to not algebraists, but algebraic topologists, who were trying to understand things. They were trying to find a so for modules we have X and Tor and stuff like that. They wanted to find a homology theory for rings, or rings over other rings, that reflects geometric properties like smoothness of a variety and stuff like that. So they understood that because of algebraic geometry, rings are very important. Because rings are very important, you want a homology theory, because homology theories usually reflect singularities, holes, connectedness, all kinds of things about varieties. So they knew they wanted a homology theory for algebras, and one of the first attempts was Hochschild's cohomology, just defined in a kind of an ad hoc way, but it's actually intimately related to the one that's kind of coming from how we're going to talk. And another one was under-equivalent homology. So, and it's in characteristic 0, it's extremely related to what we're going to talk about this week. And I might get to tell you I'm out of breath from shouting. On the last day, I might get to tell you a little how it's connected. But so many things came from topology, but here's the definition. So, yeah. Oh, and I'll say that again. So definition. Okay, here is a differential graded, which we're just going to write DG, algebra. Can you hear me?
Yes.
Good. A differential graded algebra, A is, so it's two things. It's a complex. So this part's going to look just like the old theory. So dot, 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 goes to an minus 1, differential n, dot, 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 and it goes down to a0, and then it stops. So this is differential 1 here, whatever. With, as I promised you, I want some ring structure. Well, with a product. Okay. Making the direct sum. So if you take the direct sum of all of these modules of these, oh, I should have said back here that maybe this is of abelian groups or something at this point. Abelian groups, something where you can talk about a complex. Okay. Into making this direct sum into a graded ring with, so the identity element of the ring should be in the 0th degree piece. And I guess, you know, AI times AJ should land in AI plus J. It's a graded ring. With associativity and everything else, distributivity. But now you have these two structures, and that's kind of stupid. This and this, it'd be like studying two subjects. You want it to be the same subject, linked. So you need a link between these. So such that the two structures are related. Follows? By what's called the Leibniz rule. And this, well, okay, so the differential applied to a product. You take a product in the ring, you look at where it is, and you take the differential of it. It should be the differential of A times the element B, that's what we thought, why not? Plus -1 to the absolute value of A, I'll explain what that is in a second, A partial of B. Okay, so this looks like calculus product rule, right? So something like that is called a derivation, but this has a sign in it, so it's like a sign derivation, so it acts like a derivative, and somehow that turns out to be a natural structure. And I need to tell you what the sign is. So where that is, I know some of you are going, it's not homogeneous. Hold on. Where this is the degree of A, which means, in other words, of the element A. So let me not put an A here. Of X, say, is the degree of X. In other words, X is sitting in that piece of A. So it's just where it's sitting in the complex, the homological degree. And the problem is that elements of the ring are actually direct sum, or elements in the direct sum, which means there are sums of things. They're not homogeneous. But whenever we talk about this stuff, we only talk about homogeneous elements. And for everything else, it's just extend by linearity. Okay? So all the properties I write will always be for homogeneous elements. So assume homogeneous, and then we just extend by linearity for others to figure out what is happening. Okay. Because the maps are linear over Z or over A0, so you just, okay. Right, so that's a DG algebra, but since we are doing stuff that comes from algebraic geometry in some sense, we also want some commutativity. So we also assume two things. So one is AB is equal to -1 to the degree of A, degree of B, times BA. So it's commutative up to a sign. And A squared is 0 for all A such that the degree of A is odd. One of these follows from the other as long as you're not in characteristic 2. So the second one follows from the first if you're not in characteristic 2. But if you're in characteristic 2, you have to add this. Otherwise, you never have to check this. So let me tell you what this says. If either A or B is even, then this is even, and this is gone. And then AB is BA. So if either is even degree, then they commute. Right? So AB equals BA. Okay? But if both are odd, then you get AB is minus BA, the anti. All right? Okay. So that should remind you of the exterior algebra. And this should remind you of a polynomial ring. For good reason. Okay. So some people don't call these DG algebras some people say commutative DG algebra, or even associative commutative DG algebra. So, and they abbreviate it CDGA, like that. But we will always just assume it. So we just assume. And we write, little DGA or capital DG or something like that. So I'm not going to mention the word commutative. We're just assuming it forever. Okay. Good. But if you talk to a topologist, you might want to say that you're a commutative teacher. Or other people. Okay. Great. Okay, I want to give you examples. Good. The first example is kind of stupid, but it's actually important that we know that it's an example. So if you have R is a ring, then you can just set A0 to be R and AN to be 0 for n bigger than 0. So it's just sitting in degree 0. It's a really boring complex, and it has a really boring product, namely the product in R. So you just have 0, 0, 0, A0, and that's it. So, and the ring is just the ring. Well, I guess you just have R sitting here. Okay? That's going to be considered a DG algebra, and that's important too. In order to bring the rings into the world of the DG algebras, we need a way of thinking of a ring as a DG algebra. So we're going to do this too. All right. And then my second example is the most famous example. Of a DG algebra, and which is the Kazul complex. All right, so let me remind you what it is, because again, I'm not sure if everyone has seen it using the exterior algebra definition, so I just want to review it. And also, this is going to come up all week long, so I want to review it. So K is a Koszul complex on, say, F1 up to FC on, let's call the ring R, okay? For elements F1 to FC in R. So what is this? So let me remind you. So I'm going to remind you what this is. So let F be the free module R to the C. Free. And let's call a basis E1 up to EC the standard basis. Why not? Okay? And then so then K is going to be the exterior algebra on F, wedge of F, which you could think of as, you could also write it as R adjoin E1 up to En. So this algebra, this is like an algebra generated by the EIs, so by these E's. So it's generated by a basis of F, but with degree of EI is 1. And so since we want it to be DG algebra, I wanted to satisfy, sorry, where am I? Oh, here it is. Anti-commutativity or commutativity. So all the degree 1 elements should anti-commute. So EI, EJ should equal minus EJ, EI, and EI squared is 0. So that's the module. That's what's sitting in the complex. So I need to tell you the product is from here. Sorry, that's the algebra. I'm going to tell you the differential. So with differential, the differential of E sub I1, E sub I2, up to E sub I n is the alternating sum minus 1 to the j, sum over j, of you remove one of the e's and you replace it with these elements f. So I'm going to remove the jth one and put fj. Oops, that's not right. F sub ij, ei1, eij, removed, ein. Sorry. So I removed this basis element and replaced it with the corresponding f in the ring. Okay, and you do this for all of them, and as you go along, you go plus, minus, plus, minus. All right. So that's the DG algebra. You will check this on one of your exercises. That is a DG algebra. Let me write it out one more step, like write it out. So you get wedge C of F. Because the higher exterior powers of this have as a basis more than C of these wedged together, which means one of them is repeated. And you can rearrange the order until the repeated one is next to itself, but the square is 0. So bigger than C, there is nothing. Okay, so you have wedge C goes all the way down to, I'll put wedge 2F, wedge 1F, wedge 0F. Goes to 0. And so the basis here is actually E1, E2, up to EC. Because as I said, if you put more e's, you get a square, which is 0. And also you can rearrange the order so they're in order. So this has got one basis element, so this is just isomorphic to the ring. Here the basis is stuff that looks like, so the basis of this looks like EI, EJ type stuff, with I less than J, I guess. The basis here is just the EIs, and the basis here, nothing wedged together, it's just the ring. So this one is really just the ring R. Okay, and then the differential takes EI, goes to Fi, and this guy, goes to the differential. So let's calculate the differential. Here's the differential. You remove one at a time and replace it by F. So I'm going to remove the boundary of EI, EJ is remove the EI, but Fi, EJ, minus Fj, EI. So that's the differential, this differential, and this differential, and you can calculate other ones. Okay, so last thing I want to say is that the rank of wedge IF is, well, you can write a basis down by taking the base elements of F and multiplying them together and then rearranging if necessary. So you get a bunch of E's wedged together in order and nothing repeated. So this is exactly N, not N. How many F's? C. C choose I. Okay? So that means wedge IF is really just R to the C choose I. Okay, that's the Gazoo complex. All right. Okay, so I think I'm ready to start the material now. In some sense. Okay. So first, I guess I want to say a bit more background. Okay. So sort of the interest in BG algebras sort of came from two places. I'm probably going to mess up the history a bit, but I'm trying not to. So one of them is from algebraic topology. And I just want to say like a few tiny things about it. Okay, so first place in algebraic topology, there are many complexes used to compute cohomology or homology, so homology or cohomology. So like singular chain, complex, and all those things. That have an algebra structure, that have a natural product. So what you should think of is stuff like cup products. You learned that in topology and stuff like that. You also have cat products, which are not algebra structures, but they're sort of DG module structures, which we'll also learn about. Cat products, what else was I going to say? There are also some shuffle products. Those come up less often. For example, when you do Hochschild cohomology, there's a shuffle product, and stuff like that. And the interesting thing is, which also, in fact, give rise to some inherited structures on homology. Okay? And so let me put in parentheses such as. Okay, so we have this complex in topology for computing the homology of a topological space or cohomology. usually cohomology if there's a product. And it has a product on it, so then when you go down to homology, there will also be a product. Okay? Well, that's just a plain old algebra product. But in fact, there are also invisible products that get inherited down, which I won't talk about this week, but I will mention for 1 second on Friday, such as things called Massey products that also come from the algebra structure on the complex. So something about algebra structures on complex is a much richer thing than algebra structures on homology. It gives you more than the plain old algebra structure on homology. It gives you other kind of higher product structures. So it's so that the topologists at some point realized that they needed to go backwards and go up to the complexes and study them rather than the homology. And then it went even further than that. But okay. Then there were similar structures that appeared in there were also similar things that happened structures in group cohomology and some Hopf algebra theory. And Hopf algebra, I'll just say theory. So sort of some things came up in those too. But okay, and so much of this stuff, much of the influence the development in commutative algebra. And so, okay, so even earlier than the next thing I'm going to mention. So I'm just put some names on the board. So these, if you look up papers by these people, they're really important papers. So Tate, Gullikson, especially Gullikson. Then there were various other people, and I'm probably going to forget someone. There's Asmus, Joden, Levin, maybe Shamish a bit. Then mainly I want to say Abramov and Halperin. So they did an enormous amount of stuff that's all behind everything that I'm going to talk about today. So that was already going on for a while, but parts of the commutative algebra community somehow weren't exactly getting. This was really deep stuff, but it sort of leaked into a larger part of commutative algebra with the following work. So at the level of resolution, so these were just complexes that occurred naturally. But at the level of resolutions, it sort of it started with Buchsbaum, a paper of Buchsbaum and Eisenberg. I mean, all of this existed before and was amazing, and also it did involve resolution some. But so let me say, at the level of minimal resolutions, this sort of, it didn't exactly start with them, but this renewed the interest in the community. And I want to tell you why. So here is what they conjectured. So sorry, there's I'll go in order in my notes. Okay, so here is the conjecture they did. So this is Buchsbaum and Eisenberg. Is that if so okay, there are various. Fine. If R is local, skip this one. Variously, maybe if R is a polynomial ring also. Then for any 6A module, R mod I, there is a DT algebra structure on its minimal free resolution. Let's call it F. So F is a resolution in the old-fashioned sense as an R module of R mod I. This means F is quasi-isomorphic to R mod I. F has homology R mod I, so the F is a resolution of R mod I, and this means it's free R modules. Okay. Minimal free, I should put R. Oops, put it here. R free resolution, sorry. Okay. Okay, quick note. No, I'll just say it. Okay, I'll say it. No. Okay, one can always put a product, one can always put a product on F, but this doesn't work usually, I'll tell you. But you can always try to put products with this. By lifting the multiplication on R mod I, so that would go from R mod I, like in some degree I. Well, let me just write. It goes from R mod I, tensor over R, with R mod I to R mod I. So if you have it's a ring, so even in our algebra, so you can always write that, and you can lift this to the free resolution to get a chain map from F tensor over R with F to F. And that's just because resolutions have that comparison theorem property, that if you have a map it's a bit more than that, but okay. But you can lift it to this always, and it's a chain map. And in fact, being a chain map is equivalent to Leibniz rule. So you can get what you thought was difficult was that the differential of A times B is differential of A times B, blah, 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 blah. That's easy. You can get that from it being a chain map. What the weird thing is what you're missing, but we're usually missing, or it's usually hard to get, associativity. Somehow that's the thing that's hard to get. And it's also the thing that's hard to check. To check associativity, A times B times C should be A times B times C. You have to check for all elements, or a basis at least. That's insane, usually. And also insane to kind of do it in a nice way, like we're used to doing things. So this is somehow doesn't work, usually. All right. Despite that, let me do an example to show you it's not always so hard to do. Okay? So here we'll do an example. Example. Okay. Example 3. All right, let K be a field. I mean, can we, for the rest of the week, just say that K is always a field? Okay. Now, I'm going to take the polynomial ring K of xy, so R is K of xy polynomial ring, and take the ideal x squared xy. Okay? I'm going to look at its minimal resolution And I'm kind of trying to prove the conjecture for this example where it holds. Okay. All right. So let's resolve it. I have R mod I, and I need to map a free R module onto it, so this F0 is just R. Okay. And then I need to look at the kernel of that, which is I, and map I is generated by two things. So I have R2, and so this map has the matrix x squared and xy. And that will map onto I. And then, what are the relations between x squared and xy? Can you see the relation? Something, what's the kernel of this? Something times this plus something times this should be 0.
Yeah, y times x squared.
Y times x squared
And minus x.
minus x times that one. Good. And it turns out that's it. That's the whole kernel. There's one thing in the kernel. It's generated by that. And that's the whole kernel. So the kernel is generated by exactly that vector minus dot x. The kernel of that matrix. And so I just get a single R. And then, if I have an element of R, and I send it to R times this, is it ever 0? No, unless R is 0. So the kernel is 0. So I'm done. So that's the resolution. Any question about the resolution? Because I know you're all coming from really different. Your geometers, you don't know this. Okay?
When you do the lifting, it's not unique.
So this lifting is not unique. It's unique up to homotopy. Good point. So, yeah, it might be bad if it's unique. Oh, then we're good. So if it's unique, then you could always check this. The problem is there are several lifts, and maybe you pick the bad one. That's a very good point. So associativity might hold for one lift and not the other, although it would probably hold up to a homotopy for the other. A lot of things are true up to homotopy, but for this, we want them true on the nose. So, any other? Okay, let's try to put a product structure on this. Okay, that's F0. Put it in red, blue. That's invisible. That's F0, that's F1, and that's F2. Okay, let's pick a basis, because you only need to define the product on a basis. So here the basis is 1. And here the basis, I'm going to pick E1 and E2. The usual basis, 1, 0, and 0, 1. And here I'm going to pick a basis, I think I decided to call it G. Okay, so these are the two bases of each thing. And I need to know how to multiply stuff. Okay, so it's graded. So if I multiply something times degree 1 times degree 2, I end up in F3, which is 0. So I have no choice, okay? So I really only need to define F0 times F1 and F1 times F1, which will end up in F2. And everything else will be 0. Right? Yeah. Okay. So first, let me tell you that the first thing is always the same. So for F, so we need to define, well, let me just use. We need to define a product, and we're just going to do it on the basis. And so then you can extend with our linear coefficients, no problem. All right. So degree 0 times degree 1 is always just or times degree 2. Oh, we also need 0 times 2. Okay. So first 0th step is F0, which is R, times F anything, Fi, for all I module structure. And I don't think that ever hurts. You can always do that for the 0th step. And if you're worried that if you had done it differently, it might have worked better, that's not true of isomorphism, I think. So you can always take this. In other words, 1 times anything, EI should be EI, and 1 times G should be G. And then next we need to check, what about, so what is E1 times E2? Okay, the 2-degree one thing. That should land in, this lands in degree 1 times degree 1 should land in F2. All right. Why am I not checking E1 times E1? It's 0. Okay, yeah, E1 squared is 0 because it's an odd element, so it's square 0. So I probably should have said, define E1 squared to be 0. Maybe I should say it. Let EI squared be 0. That's sort of. Okay, so what do we want? We want an algebra, blah, blah, blah. We want the Leibniz rule, right? So we want the Leibniz rule to hold. So let's take the differential of E1, E2, and we want that to equal the differential of E1 times E2. Those of you who have not seen this before, tell me. Minus. So that's because the degree, well, let me write it out. Plus minus 1 to the degree of E1. So what you're doing is you're passing the differential over E1. And as you pass it over E1, it gains a sign of minus 1 to the, of minus if it's odd, plus if it's an even element. So I get minus 1 to the degree of E1, so that's just minus 1. E1.
The
Differential of
Partial of E2. Okay, so it's the product rule. That's fine. All right, and then what did E1 go to? Under the map?
X squared.
X squared. So I get X squared E2 minus, because that was minus, and E1, and what was this one?
XY.
XY. So XY, E1. Back, degree 0 elements commute with everything, so I'm just going to put it in front. All right. I'm trying to figure out what E1, E2 is. I know the differential of it, and now I want a pre-image. So what is this the differential of? Let's look. So I'm sitting where? I multiplied them together. Wait.
Isn't it like minus 6 times?
Sorry, it's here, and then took the differential. Right. Yes, let's pull out the minus x. It's, okay, fine, I put it inside. Yeah. Minus x
Times G.
times g. Yeah, so maybe I should do this in 2 steps. So this is minus x times x e2 minus y e1. So that's minus x
No,
partial of g.
you're missing a sign. It's minus 6. And then y times C1 minus.
Minus SE2 plus.
Oh, I did sign changed.
Yeah, yeah.
Sorry. Oops. Minus this plus this now.
That's correct.
Okay, and so that's the partial g, and I guess it's r linear, so let me pull it inside. It's the partial of minus xg. Okay? Good, so we know that the Leibniz rule to hold, you need this. This is what you need to be true. Well, so why not just define E1, E2 to be this thing inside? It works. So let's just define. We can do whatever we want as long as it works eventually. E1, E2 to equal minus xg. Okay? Now, actually, in this case, this last differential, it was this one is injective, so there's only one choice. It's unique, okay? This was actually the only choice, so this was actually the unique choice. Since partial 2 is injective. All right. And that's actually that was a kind of idea exploited by people. So what do we need to show? Well, we've shown Leibniz everywhere where you would like to have it. I mean, it's easy to show for this too. What's missing? What did we not show? Oh, associativity, the thing that's so hard to remember to show. Associativity. Okay, so I want to know if A times BC is equal to AB times C. Now, so you can just look at homogeneous elements, and you can just look at basis elements. So, enough to show for basis elements. And in fact, for anything coming from F0, I guess the basis is 1. It's obvious. Okay? So if A, B, or C is in F0, it's all obvious. Okay, so what's the only interesting thing maybe is if we're at least here. So 1 times 1 times 1, where are you? F3, which is 0. So both sides are 0. So there's nothing to check. So, but all triple products in F bigger than 0 degree land in F bigger than 3, which is 0. Oh, bigger than or equal to 3. Sorry. Okay, so this is automatic. So done. Both sides are equal. They're both 0. Okay, so it's not so hard to put a structure. Well, associativity is hard usually. But okay, so people thought, oh, maybe you could do it. All right. So their conjecture. So Buchstaben and Eisenberg conjectured that this could always be done in 1977. So BE was in 77. But it turns out that actually there was already a counterexample before that. But they didn't know about it because it was in an appendix to a Russian paper before the internet. So okay. So, but it was from a key player in the game. So he actually wrote to them. So there's something in the paper that says this. So unfortunately, this cannot. That's 1 hour. This cannot always be done. Oh well. And so Abramov in 1974 gave an example, or a counter. Okay, and then, in fact, there were more and more counterexamples. So let me give you some of the counterexamples. But then I want to remember to go back to Buchstaben and Eisenberg for a minute. I skipped something by mistake. Okay, so first place, there's Abramov's example in 74, but then in 81, he proved an even bigger result that showed that, in fact, there's an element in something that you can compute that obstructs there being a DG algebra sometimes. So he gave obstructions to existence of DG algebra structures. And so that renewed a lot of interest. So there were obstructions, and it involved maps of Tor modules and quotients. So anyway, so it doesn't always exist. But then there was still a question of when does it, and there still is the question of when does it. People don't know. But there were other examples to push and show just how badly it fails. So Srinivasan in her thesis in 92, and then also more in 96, found examples with projective dimension of R mod I equal to over R equal to 5, non-Gorenstein. Oh wait, I'm on the wrong line. Sorry, Gorenstein. That doesn't make sense. Okay. And in fact, the second example had a vanishing obstruction. Ramos obstruction vanished, but still you couldn't put it. Even there wasn't an obvious reason you couldn't put it in the algebra structure, but you actually can't. You proved it more directly. And then really recently, Katan gave a really nice, in 2018, gave a monomial example, which I find really nice. Monomial ideal. That has this property. So there are lots of examples, okay? And even with really short resolutions. Ramos is projective dimension of R mod I is 4. So even pretty short resolutions fail. But there are some positive results. Okay, let me do this one quickly. Projective dimension, really, really short, like the example we did. Projective dimension less than or equal to 3 is, if it's 2, it's Hilbert-Birch. If it's 3, it's a Buchsbaum-Eisenbud-Papien resolution. So the resolutions are known. Structure of the resolution. So this uses the structure of the resolution, which is known, and then you can put a DG algebra structure really easily. The hard part is understanding these resolutions. So that was, there's Hilbert-Birch theorem, and there's also the Buchsbaum-Eisenbud structure for projective dimension 3. Well, so for Gorenstein. But then they also proved for, without that structure theorem, that it's also.
You want Cohen Macaulay the first?
Yeah, well, that's a good question. You want Cohen Macaulay? Wait. That's a good question. I don't know the answer. So do you need these to be perfect modules? I don't remember. Does anyone know? No? No, I think don't. Okay. And then also projective dimension of R mod I is 4, and it's a Gorenstein ring. Okay, so I should have said, so let's say a Gorenstein ideal. For example, if the ring is regular and the ideal, and R mod I is a Gorenstein ring. Okay, but there's also more general I is Gorenstein ideal. Then Kristen and Miller, not me, the different Miller, says this. So, anyway, then there are lots of common. It's interesting because it actually is quite persistent. It happens a lot in rings that come from combinatorial settings. So, combinatorial examples, often things do hold. So you can have the Taylor resolution, if you know what that is. The Eliahu Bear resolution of Borel fixed ideals. So the second, I'm not going to write on the board. In the notes, eventually, someday, type, there will be the names. So this is Peva, the second one. And the first one is by someone called Gameta, I think. So, and then powers of the maximal ideal. There are a few other things where things are known. But mostly, this is wide open. Wide open. So let me tell you why, even though it fails, and it seems like we're just doing this for no reason, there's a good reason for this. to want this to be true. So it's still wide open for what ideals you can get a DG algebra resolution. And it's interesting because it gives you an answer to a famous conjecture. So I want to talk about that. Okay, so although it's false in general, okay, it is true sometimes, and so BE, Buffon Eisenbud's motivation for it is still interesting. Their motivation was an exciting new approach to an old result called Porous Conjecture. Which came from the world of algebraic geometry. And it says that if R is the polynomial ring, x1 through xn, by the way, all of these examples and positive results are over the polynomial ring. R is the polynomial ring for all of these. Yeah. So, over the polynomial ring, if you have M is a graded R module, with finite length, and F going to R over R to F. So F being a minimal free resolution. Free R modules, we know free resolution of F. R modules. Then the rank of the ith module is at least the number of variables n choose I. So they could see this in examples that they computed, but it's a very difficult conjecture. It's one of the biggest conjectures around. It's wide open. Well, it's fairly open. And what Buffon and Eisenbud showed is that if you have an algebra structure, you get this. So they showed, well, they did it even more generally. So let R be a domain, I an ideal, and F goes to R not I of minimal free resolution. With a DG algebra structure. Well, we just saw there are counterexamples, so you don't always get this. But you often do. So if you have that, then, and the Kazoo complex, K is the Kazoo complex on F1 up to FC on R, where F1 to FC are in I and are a maximal, I should just say the other order, sorry, a maximal regular R sequence in the ideal into free resolution. So this uses the algebra structure, right? This is the sort of generated by E1 up to EC. This is the Kazoo complex. It's actually kind of a free algebra. This is something we're going to see later this week. It's a free DG algebra. And so it can map the E's to the obvious kind of in F1. Then you get a map very easily. But they proved that it's an injection. And if it's an injection, the rents here have to be as big as the rents here. And these are exactly how big you want them to be. Okay? So the rank of Fi is bigger than or equal to the rank of Ki, which is exactly n2 psi. All right, so getting a Kazoo complex in there seems like a great way to show that Horrocks is true. So then in Horrocks' original version of the conjecture is a finite length, so you can take a regular sequence of length n inside of it and get Horrocks. So Horrocks follows in that case. Okay. What else do I want to say? I don't have much time. Oh, I do. Why don't we take a 1-minute break? And breathe. I never know if I'm going to make it, so I'm going to... Okay. Yeah, okay. Okay, so last I want to tell you just 2 technical things. What is a DG module and a semi-free DG module and a lifting lemma that's going to help us lifting maps. Okay. DG modules. And I'll also tell you about semi-freeness. Okay, here's a DG module. It's really almost the same as DG algebra, but you don't need a ring, you need a module. Okay, so I'll write it out. Okay, so given a DG algebra A, so you know it's a complex and it has all these parts, A sub n bigger than or equal to 0, and it has a multiplication and a differential. Okay, let's make a module over that. A DG A module. M, which looks like a bunch of MNs, n bigger than or equal to 0, is a complex that looks like ... Mn, partial n, ... M1, M0, and that's partial 1. Now, for an algebra, we stopped because you really want an identity element in degree 0, and you want things positively graded for an algebra, unless you localize, whatever. Let's not talk about that. And then, but here, this can go on forever, and -1 and so on. Okay. Wait, I think. Yeah, okay. Not what I wrote in my notes, but it can. Okay. Again, such that M, we write it as M. Sometimes the direct sum of all these MNs, n bigger than or equal to 0, is a, oh, sorry, I should have said, has a product A cross M to M, or a pairing, such that, or making M into A and A module. Okay? So when I'm not done, but yes?
I have a question. So the point is that like the DG module is just the positive and non-negative and
No, oh, thank you. Sorry, I just fell asleep. Okay. Thank you for asking. No, this is over all n. Okay. N is Z. Thank you.
so for the n is the set of mn.
Yes, it should be all n in Z. Thank you. Thank you. No n bigger than or equal to 0, just all n of them will stop here, but sometimes we shift things and they don't stop here. Yes, thank you. All the n's should be over all integers. Any other? Okay, and we have a complex. How beautiful. We have a product, so this makes M an A module. We have a way to multiply A times things in A times M things in M, and M. And again, they have to be compatible, so such that you get a Leibniz rule. Leibniz holds. And so in this case, what kind of things are you multiplying? You're multiplying things in A times things in M. So you just need the same thing as usual. So it's the boundary of A times M plus minus 1 to the degree of A boundary of M. And just to repeat, in case you missed it last time, what happens is we first hit the first element with a differential, then we move it across and hit the second element, and when you do that, because you moved it across A, you get a minus 1 to the degree of A. That just makes all the signs work beautifully. You do that. Okay, so that's a module. Okay, fine. A morphism of, and I did not define that for algebras either, so I'm going to do algebras and modules at the same time. So of DG algebras or DG modules, respectively, is A. So it needs to be a map of complexes, because you have two complexes, so that's called a chain map. It also needs to be a map of, if you have two algebras, they're rings, so a map of rings. So a chain map that also gives a homomorphism of algebras or rings over some base ring. Okay, except for DG modules, it would be a homomorphism of modules. And now I should have said the DG modules would need to be over the same DG algebra. Let's say A, and so this would be a map of A modules here. So I changed this up here. The two modules need to be over the same algebra. And this is a map of, in parentheses, of modules over that same algebra A. Okay, and what is, so let me go on to semi-agreement. So the next definition is, so we, just like in usual resolutions, we would really like to work with free modules. So here's the corresponding notion, kind of. Is so if A is a DG algebra, and M is a DG A module, okay, we say M is semi-free over A. If so I'm going to write M, and I'm going to put a little symbol here that will explain in a second, is a free A, same symbol, module. If you know music, which I don't know, this is a natural symbol. I know enough to know this is a natural symbol, which means you forget something. Forgot what. And so what we're forgetting here, this means just think of it as a module in an algebra, forget the complex. So forget the differential. Just think of it as a module in an algebra, and it's a free module over here. Okay, but that's a little, right, so that's when it's semi-free, but the case that we're going to have the most is if A just A0 is just R, a ring. So if you have a very boring DG algebra A, but possibly an interesting module M with complex, with differentials, that we're going to have a lot. Then M is semi-free, just is the same as saying each MI is just free R module. So it's just a complex of free R modules. That's what it will usually mean for us. Yes?
Don't you want
Probably.
that to be semi-free when M's comical love? Like,
Sorry, that would
otherwise
be
you
semi-free one.
Yeah, when M's comical love, but otherwise you need a semi-basis, right?
Oh,
So
otherwise you need what?
semi-basis, right? Like you need the filtration, but
Oh.
maybe make M comical love.
Okay.
And then it should be okay.
If M is M bigger than or equal to 0.
Or
Thank
something
you.
like that.
Yeah, okay, or above it at some point up. Right, so if you have a doubly, if you have an unbounded below module, you have to define it a little more carefully with filtration. I don't know that stuff. Okay. Good. And the last thing I want to say is that these look pretty cool. If they have, let's just take a boring A. If you have a DG module over A, it's got all these nice free modules in it. You think maybe you can get a projectivity property or a free mapping from here. So you almost can. So it's not free, so although, if M, sorry, hold on, this I say. Although semi-free DG modules are, or even complexes, whatever, are not, they're not projective or free. They're not projective in the category that we're working in. I mean, I don't even have to say DG modules. Let's say bounded below complexes. So in this case, they're not projective in the category of bounded below complexes. So it's hard to get maps from them, it would seem. They do, you still have a weaker property that's almost like a projective. You do have the following weaker property. Right? So I'm going to call this lifting lemma number 1. It helps us get maps. So if you have A is a DG algebra, F, I'm going to call F instead of M because it is semi-free. A DGA module. Then I'm almost done. Then for all M and N, M and N, whoops, DGA modules, and morphisms F and G in the following diagram. So let me write a diagram. So we have M surjectively onto N. We'll call this map F. So for all maps F here, and I want them to be surjective and quasi-iso. So that means isomorphism on homology. I defined it in the first few minutes of lecture. Okay, but you can go back and look at that. And any map G here, that's a DG module map from F, it will lift to a map to the bigger thing by a map. There exists a map, so for all F and for all G, there exists an H here. So there exists, let me write on the next board. There exists a map, and it's kind of unique-ish. So hold on. which is something kind of new in this situation. There exists an H. It's a DGA module morphism, of course. And in fact, it's kind of cool that H is unique up to an A-linear homotropy. And that's even something you don't get back in the world of modules for a projective module, but that's because these are not very... In the world of projective modules, you have a projective module and a map of two modules, projection, and then you can go up. But in that world, well, first place, there aren't any complexes, so how much would be? But anyway, the lifts are not unique because these two are not usually very closely related. It's just a projection. We have a quasi-iso. So in actuality, these are sort of related. And because of that, this lift is unique up to homotopy. Okay? And you might want to, if you prefer this diagram sideways, rewrite it sideways. M goes on to N. It's a quasi-iso and it's surjective. And then we have a map from this semi-free here, and we get there exists this map H. I mean, that's still like the old-fashioned, right? It was projective for a long time. I didn't like them, and now I like them. Anyway, what became F? This one's F. Okay, that's it. So, if you have questions, just come and catch me. Okay? On simple things.